Okay, good morning. Today we're going to start talking about Chapter 10, and the title of Chapter 10 is Correlation and Regression, which represents the last two major topics we're going to talk about in this semester. And today we're going to talk about Section 10.2, which is entitled Correlation. Well, first thing we have to do is define what correlation means. A correlation exists between two variables. So we'll see our data sets here are going to be bivariate, or have two variables represented, in other words, paired data values. A correlation exists between two variables when values of one variable are associated with values of another. And that's more or less the textbook definition, and they are being purposely vague when they say associated. Perhaps an example would help us make the situation a little more clear. This data set, paired value data set, is out of the chapter problem on page 517. And what they do in this paired data set is track the cost of pizza against the cost of a subway fare in New York City from years 1960 to 2003. And they don't do it every year. Let me fill in these values. Again, this data is in the book on page 517. This pair was taken from 1960. This one from 1973. Give me a minute to write this down. This pair of data was from 1986. This pair from 1995. This pair from 2002. And this pair from 2003. Alright, and these values, these costs are in dollars, of course, and for more detail we'll ask you to refer to chapter problem at the beginning of chapter 10 on page 517. Alright, so in these paired data values of pizza and subway cost from years 1960 to 2003, well, I think we can infer from this sample of paired data that there is an association between these two variables, pizza cost and subway fare. I might suggest that there is a positive correlation between these two variables. Let me write that down. I'm going to suggest there's a positive correlation exists between pizza that's per slice cost and subway fare in New York City in the years specified. Alright, well, what do we mean by positive correlation? Well, in wide strokes, that means as pizza goes up, subway fare would go up. Alright, so let me sharpen up that concept of positive correlation. If we graph what we call scatter plots of pairwise data, well, we're always graphing one variable against the other, so you can have a two-dimensional graph here. If I get a scatter plot of data values that looks something like this, this suggests a strong positive correlation. meaning as one variable value goes up, the other tends to go up. All right, what might a negative correlation look like? The scatter plot of paired data that exhibit a negative correlation. Well, I think you know where we're going here. If one variable is x and one variable is y, well, that means one variable value would go down as the other goes up, and that might be the tendency for a negative correlation to look something like that in terms of scatter plot. Okay? All right, no correlation. Well, if there is a situation that might emerge, might be no correlation between data values, and in that case you see no upward or downward trend. Basically, data values are all over the place, high, low, in between, with no discernible pattern existing between y and x. Okay? Alright. Now, different paired data values will have different levels of correlation. Well, the next question we want to ask is how to measure correlation. And there will be a measure of correlation that will enable us to tag a number right onto it. We're going to measure the correlation with something called R, lowercase r, and that is the accepted terminology or symbology for linear correlation coefficient. Okay? Little r. And it measures the strength or lack of it of a linear correlation between two variables. Okay? All right, now there is a formula for R. If you're given two variables x and y with different pairwise values recorded in a sample type process, R can be computed according to this formula. Of course, where summation xy means the pairwise products of x and y values added up, and summation x and summation y are, of course, the sum of all x values and the sum of all y values. In the denominator, we've got two square root expressions, and the symbology should look somewhat familiar to you regarding earlier formulas we've seen in this course. Alright, we are neither going to prove nor use this formula, at least directly, because the calculator computes this for us. The TI-8384 calculator will compute your linear correlation coefficient R. Alright. What about R? Facts about R. Well, if you stare at the formula for R long enough, you should be able to talk yourself into the fact that for any pairwise data, R can be a minimum of -1 and a maximum of +1. Alright, what we're going to do in using R, we're going to determine critical values for R. Left and right critical values for R. And if I am left of this negative critical value for R, I claim there will be a strong negative correlation between the pairwise data values. Similarly, if my value of R from data is beyond the right critical value I obtain for R, I claim there will be a strong positive correlation between the pairwise data. And if my value of R, I should say, arrived at from data, is in between these critical values, I claim there is no correlation or no significant correlation between the pairwise data values. Alright, so in wide strokes, that's where we're headed today. Let me show you how to compute R from the calculator. How to compute your linear correlation coefficient. Well, first, we've got to make sure that your diagnostic, we have to set a function on your calculator called diagnostic on. Now, I'm 99% sure that everyone's calculator has this function on, but if there's been a reset on your calculator, it may have been turned off. So let me show you how to set your diagnostic on your calculator. Hit the second gold button there and then catalog. Now the catalog function is right above the 0 button on your calculator. Above the 0 button, okay. Alright, what this does, it lists all available functions on your calculator in an alphabetically sorted type list. Alright, after you hit catalog, scroll down to choose diagnostic on. You'll have to scroll quite a ways. Make sure that function is selected with an arrow and then hit enter twice. What that does, it calls up the diagnostic on command into your home screen, and then when you hit enter again, it executes the diagnostic on command, and you should be all set to go to compute R once you turn diagnostic on. Okay? Alright, now we want to clear out the old data and enter in our new pairwise data. And to clear out the old data, you may recall we hit Stat, Edit, and you'll see your data in list from L1, typically from L1 to L6. And I'll ask us to clear L1 and L2. You'll recall how to do that. And enter in, well, we might as well go with the pizza data in L1 and the subway data given in the chapter problem into L2. Okay. Let me get a fresh screen here. Alright, when you're ready to compute R, when you've got your old data cleared out and your new data entered in, then we'll again hit Stat and hit Stat, then scroll over to Tests. And we've done that before in this course. And here's a new command which is going to enable us to view R. It's called the linreg t-test. Linreg for linear regression. T because we're going to base this value of R on a t-score. And test because it's in the test submenu. Alright, the calculator prompts us for some things. Well, it asks us where is your X data, and I believe the default is L1, so hopefully we put our pizza data in list L1, then prompts us for a Y list, and I'll put in my L2. Hopefully that's the default for the Y list L2. There's some other things which we'll pretty much leave unchanged. The frequency is 1. That's fine. There's a beta and row option I'm going to ask us to ignore, at least for the time being. Also, this command, regeq, I'm going to ignore that for now. And the result screen will look something like this. Well, there's a lot of information, and all we're interested in for the purposes of this section today is to scroll down to see R. R is what it's all about for establishing correlation. All right, for our pizza and Subway data, we get an R value of 0.988, and if you take a look at that data, you might guess that there is a strong positive correlation, and you can't get much stronger than 0.988. Again, 1 is what they call a perfect linear correlation, so almost a perfect linear correlation here. All right. Interpreting R. Well, we've got an R value here of 0.988. How are we going to interpret that? Again, if we look at R values, they have to be between -1 and 1. What I need to do is establish critical values for R. Now, you'll have typically a positive one and a negative one. If you're greater than the right one, you've got a strong positive correlation. If you're less than the left one, you've got a strong negative correlation. How to determine these critical values? Well, we're not going to use the calculator for this. We're going to use Table A6 on page 760 in our book. So why don't you get your books out and turn to that page, and I'll go on from here. If you look at Table A6, you'll see something like this. Basically, it's a 3-column table. You've got n values from 4 to 5 to 6, ... You've got an alpha equals 0.05 column with certain values listed. Let me write a few of them. And if alpha equals 0.01, you've got other options for your critical values here. So the main body of the table here, as you might expect, is the actual critical values, right? Kind of sorted according to your sample size. All right, for the pizza Subway data, I'll say find the critical values for R at a 0.05 significance level. All right, so alpha is going to be treated much like it was treated in Chapter 7 and Chapter 8. Basically, our burden of proof, our height of the hurdle that we have to overcome to establish some sort of linear correlation claim here. All right, so for the pizza Subway data, I believe we have 6 pairs of data. So I look under n equals 6, and under n equals 6 and alpha equals 0.05, well, I can look in Table A6 on page 760. If n equals 6 and alpha equals 0.05, that means I've got a critical value for R of 0.811. Now you may ask, what about the negative critical value? Well, if you read the bottom of the chart, there's a little clue. You really want the positive and negative value of 0.811 for our critical values. So my critical values for R from this table is going to be plus or minus 0.811. Okay, just take the positive and negative value established in that table for your particular significance level and, of course, number of pairs of data values. All right, so what I've got here now if I draw a little graph of possible R values, I'll label my critical values for R. And remember, if you're in this region, you've got a strong negative correlation. If you're in this region, you've got a strong positive correlation. And if you're in between, we claim there is no significant correlation. If you'll recall, your R value here for this data was 0.988. So what I'm going to do is draw what I call a verdict arrow. And that was from our sample data. Right? And of course, I'm in my right critical region. Okay? So I claim, based on this table, based on the sample data, that a strong positive correlation exists between cost of pizza slices and subway fares between the years 1960 and 2003. And I suppose I should state the significance level here, because your answer might change depending on your significance level. Alright, so strong positive correlation exists at alpha equals 0.05 for our pizza and subway data. Okay. Alright, so as usual, the calculator, the technology takes away a lot of the drudgery and we can turn our minds to higher things. I want to look at number 16. 16 is in your homework list, page 532. Let's take a look. 16, page 532. Alright, it talks about heights of presidents and their runners-up in presidential elections. Let's read the problem. Theories have been developed about the heights of winning candidates for the U.S. presidency and the heights of candidates who were runners-up. Listed below are heights in inches from recent presidential elections. Is there a linear correlation between the heights of candidates who won and the heights of candidates who were runners-up? Alright, so you'll see in the book they list the raw data. So you got the winners here and this row, and let me take a minute to copy them down. 69.5, 73, 73, 74, 74.5, 74.5, 71, and 71. Alright, notice it's kind of hard to predict from looking at this raw data because this data is not sorted in the lists. So let's see, runner-up, I'll just abbreviate that RU, and heights in inches, 72 inches, 69.5, 70, 68, 74, 74, 73, and 76. Alright, so we want to establish whether a linear correlation exists in this data set, in this pairwise data set. Alright, so what I'm going to do is go to the calculator. I'm going to ask you to compute R, your linear correlation coefficient. Now that's fairly tedious. Enter or clear out the old data, enter the new data, Go to our new calculator command, the Linreg t-test. But once you do all that, we should come up with an R value of negative 0.221. Alright, now it is negative, so that may infer a negative correlation may exist in these paired data values, but it seems it might be a little weak because you can go down as far as -1. Alright, well, this is our sample. From our sample data, little r is minus 0.221. So now we'll compute, or really use the table, to find the critical values for little r. Now, the book says to use 0.05 level of significance on this entire set of homework problems. If you read the instructions for all these problems in this set, you'll see they say to use alpha equals 0.05. And of course, our sample size is 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 pairs of data. So if I look under 8 pairs of data in that row in table A6, under 8, under alpha equals 0.05, I get critical values of plus or minus 0.707. Okay? Alright, so that's going to determine the bar, so to speak, the height of the bar, the hurdle I have to overcome to establish whether a significant correlation exists or not. Alright, so I'll draw my little diagram for our values. 0.707 positive and negative are going to be my critical values, beyond which I will claim a correlation of some kind. Now here's my verdict arrow, negative 0.221. Well, probably a good idea to put 0 somewhere in the middle here to establish a kind of a milestone. In any case, this is not in my critical region. I'm going to label this is a verdict arrow. Right, for my R value from sample data. So this value for R is not in either of my critical regions. So I claim the sample data is not significant, and I would just make a conclusion like this. The sample, interpretive statement perhaps, my paired sample data indicate no strong correlation between the heights of winners and runners-up in presidential elections at alpha equals 0.05. So, and the long and short of it is no strong correlation indicated at alpha equals 0.05. Alright, so we're approaching the 29-minute point. I'm going to call it a day, and be sure to grind out that homework and get comfortable with that Linreg t-test command. We're going to need it. The next thing we're going to cover is regression, and do still more with the calculator. Alright, that's it for today.